Alright, for today's pre-lecture video, we're going to look at the energy stored in a capacitor. So, the energy that's stored in the capacitor is basically a byproduct of the amount of work that we have to put in order to get the capacitor fully charged. So, let's write that down. So in this picture here, we have a capacitor that's charged. The blue lines, of course, represent the electric field, so that allows us to infer that the left-hand plate is the positively charged plate, and the negatively charged plate is on the right. Right now, this capacitor has sort of an intermediate charge, and so we will say that on this side we have a positive little q and a minus little q on the negative side. And the reason that I'm writing negative q is to differentiate it from the total charge, which we would give the symbol big Q or capital Q. And so right now that capacitor has a potential difference of V, but again we'll say that its potential difference is a little v. And so it's kind of hard to differentiate little v's and big V's, but we'll just call it little v, again, to differentiate it from the potential it has when it's fully charged. And so now what we're going to imagine is we're going to imagine a little positive dq, but we're going to take it and we want to move it from here over to here. And so that actually takes work because the positive charge wouldn't really want to go there. We're working against the electric field. So we're doing work by some sort of external force. This is not happening by virtue of the electric field force, or Q times E. It has to be some sort of external force. Now, the amount of work that we do every time we move a little bit of charge dq is equal to V dq. And it's the idea sort of goes around the idea of the potential energy is equal to Q times delta V, but you might think that there's a negative sign missing. It really isn't, because we're not talking about work done by the electric field, but again, work done by an external force, which would be working in the opposite direction. So the total work, which is going to be equal to the energy that will be stored, because as we are doing that work, we're giving energy to the system, is going to be the integral of V dq when Q goes from 0 to big Q. Now, the potential difference across the capacitor at any instant in time is going to be related to the amount of charge on the plate and the capacitance. And so if we write the relationship for capacitance, we can rearrange it, and it's going to be Q over C. And so we're going to rewrite this as, and we'll write it as a little q again to differentiate, over C, 0 to Q. And so when we look at this and we integrate it, we're going to get Q squared over 2 evaluated at 0 and positive Q. And so the work done in order to charge this capacitor to a full charge is going to be equal to 1/2 Q squared over V. That's just one way that we can write the expression. Oh, not over C, over V, it's over C. What am I doing? So it's Q squared over 2C, and we can rewrite this a couple different ways using the relationship for capacitance again. And so another way to write it is equal to 1/2 CV squared if we get rid of the Q. And then we can also get rid of the capacitance term, can also be written as 1/2 QV. I always feel like you only need to remember one of these, and then using the idea that C is equal to Q over V, you can eliminate whatever variable you don't have. But in any case, these expressions become the energy that's stored in the capacitor. Now we say that the capacitor stores energy and it's stored in the electric field. Let's take a look at what that means. So energy density, and we represent this as a little u, is energy stored over volume, so it is a true density. And now let's imagine we have a parallel plate capacitor, and we're going to write the energy stored in our capacitor as 1/2 CV squared, but our volume, the volume between the plates of a parallel plate capacitor will be the cross-sectional area of the plates times the distance between the plates. Now let's write the expression for capacitance of a parallel plate capacitor. And so it's epsilon naught A over D. This is going to give us epsilon naught V squared. The A's are going to cancel out, and we're going to get 2D squared. But now, remember that the potential difference between the plates is related to the electric field times the distance. And so the energy density, again, we could replace V squared by E times D squared over 2D squared. The D's now are going to cancel. We're going to get 1/2 epsilon naught E squared, and this is the energy density. And so you see that what we ended up doing was showing that the energy between the two plates is really exclusively related to the electric field, and that's why we can say that it's due to it's stored in the electric field. Now, we can go through a couple of pretty good conceptual type questions when we're talking about the energy stored in a battery, energy stored in a capacitor. And so there are two rules that I want you to remember when we approach these questions, because it's really key that you remember these things in order to be able to answer the question correctly. So the first thing we need to remember is if a capacitor stays connected to a battery, and that is, in all the cases that we look at, in order to fully charge the capacitor, the first thing we need to do is connect it to a battery, and that will give a potential difference across the plates, and it will allow the capacitor to charge up until it has the same potential difference. And then remember that the charge that the capacitor will have will be related to whatever value its capacitance has, because the charge to voltage ratio has to be equal to the capacitance of the capacitor that we connected. So, keeping that in mind, if we keep the capacitor connected to the battery and we actually start to try to do something to the capacitor, whether it be maybe pull the plates apart or push them closer together, because it's connected to the battery, it will maintain that potential difference no matter what. And so we have to keep that in mind. The second possibility is if we take a capacitor and we charge it up, but then we disconnect it from the battery, in that situation, the thing that has to be the same, that can't change, in this case, is the charge on the capacitor. It's simply because the charge has nowhere to go. So I want you to notice that in these two situations, there's always one thing that can't change. When we keep the capacitor connected to the battery, the potential can't change. If we disconnect the capacitor from the battery, the charge has to remain the same. So keeping that in mind, let's look at this question. We have a parallel plate capacitor connected to a battery of voltage V and fully charged. Then we disconnect it from the battery and the plates are pushed together to half their original separation. And we are asked, what happens to the energy stored in the capacitor? Well, if we think about originally, the capacitance is equal to the charge over the voltage. And so we could write the energy stored. We could write it a lot of different ways, but one of the ways we could write it is the energy originally is going to be 1/2 times that original capacitance times the original voltage squared. Okay, so this is at first. Okay, so then it says it's disconnected from the battery. And so keep in mind, what does that mean? Because it's disconnected, that means that the voltage can change, the charge does not change. And the reason the charge can't change when we disconnect it from the battery is simply because there is no way for the charge to leave the plates. And that's why it can't change. And this also will mean that the electric field will remain the same because of the charge. So when we take the separation of the plates and they go to half of their original separation, that also means that the potential difference is going to be half of the original potential difference. All right, and so let's just keep in mind, so we said the energy originally is 1/2 C0 V0 squared. We said V is going to go to V0 over 2 because D went to D0 over 2, and that's why. And so now our new energy is 1/2 times the capacitance. And now so we have to ask ourselves, does the capacitance change? And we learned on the first day that we talked about capacitors, if we physically alter the capacitor, we can change the value. And because capacitance is change over potential, a charge over potential, by decreasing the potential, we actually will change the capacitance. So C is going to be actually twice the original capacitance. And so we'll remember that. And we said that the new voltage is half of the original. So we have V0 over 2 squared. And this is how we're going to write the new energy. So we have 1/2 times 2C0 times V0 squared over 4. And notice that this is going to be equal to 1/2 C0 V0 squared, and then times a factor of 1/2. So the new energy is equal to the old energy divided by 2. And so our energy has actually decreased by a factor of 2 by changing this capacitor. We'll look at some other problems like this in class, and we will even do them with dielectrics. So it's something that we're going to talk a lot about to make sure that we understand what changes on a capacitor are going to affect it, and how, depending on whether or not it stays connected to the battery.